Einstein's Relativity, the Special Theory and the General Theory. Chapter 9, Relativity of Simultaneity. New Modern Translation 2025. Albert Einstein and Harry Yoon, Translator. Introduction, Chapter 9. This chapter is a continuation of the previous chapter, the concept of time in physics. Chapters 8 and 9 should really be viewed as a single chapter. In the previous chapter, we first learned the concept of the same time, or simultaneity of two or more events, according to Einstein's special theory of relativity. And based on this concept, we learned how to define time, across distant points in an inertial reference frame, that was consistent with the special principle of relativity. In this context, we also made an important assumption that time runs at the same rate at every point in the same reference frame, which can be viewed as inherited from Newton's idea of absolute time. This is one of the most neglected aspects of Einstein's idea of time. Now, in this chapter, Einstein goes on to show that the concept of the same time is relative, and hence time itself, according to its definition in special relativity, is also relative. This is what ultimately differentiates Einstein's time from Newton's time. The title of this chapter is Relativity of Simultaneity, which many of the readers may have heard of who have had some exposure to special relativity before. This is one of the most basic concepts in the special theory of relativity. As we emphasized in the previous chapter, the word relative in the current context means relative to a particular inertial frame of reference, or relative to a particular inertial observer like you and me, as long as we are not accelerating. So this is our first step into the strange and peculiar world of Einstein. All textbooks on special relativity start more or less from this concept, relativity of simultaneity. Not to be mysterious or anything, but relativity of simultaneity is not about time. Or at least it's not just about time. We hope that all readers will have understood what this statement means after reading this chapter. There are many paradoxes in science in general, but in particular, there are a lot of them in the context of relativity. We include a few such paradoxes in the translator's appendices throughout this book. First of all, what is a paradox? In English, this word includes various meanings, such as contradiction, inconsistency, and absurdity, among many others. Whenever people, even well-trained physicists, talk about paradoxes in special relativity, they almost always start with a disclaimer that the ABC paradox is not really a paradox. This is because of the strong connotations of the above-mentioned meanings in the word paradox, as commonly used in English. However, when we say paradox in relativity, and in science in general, this word does not necessarily mean contradiction or absurdity. In fact, this word originated from the Greek word paradoxa. It was the ancient Greek philosopher Parmenides of Elea who first coined this term. Parmenides had a dualistic philosophy, which likely influenced Plato, for instance, in which the world consisted of its true nature and its appearance, doxa. The word paradoxa meant something that was contrary, para, to what it seemed, doxa. Hence this word, in its original meaning, did not mean that something was a contradiction or it was incorrect. It simply meant that something would turn out to be different, if you really understood it, from its appearance, that is, its appearance at first sight. There are many well-known paradoxes in special relativity, such as the clock paradox, aka the twin paradox. In the appendix of this chapter, we will discuss a couple of them, namely Einstein's lightning paradoxes and Roger Penrose's Andromeda paradox, both of which are directly related to the concept of simultaneity in special relativity. As we alluded a few times already, despite its ultimate simplicity, special relativity is one of the most misunderstood theories, not only among the popular audience, but even among the well-trained professional physicists. This kind of paradoxes can help you test your understanding of special relativity. And paradoxes are always fun. Chapter 9, Relativity of Simultaneity. In the thought experiment of the two lightning strikes on a straight railroad track, in the previous chapter, we based all our considerations on one particular inertial frame of reference, namely the railroad embankment, or the ground. Let us now suppose that a very long train, as schematically shown in the figure below, is traveling on this straight railroad track with a constant speed, v, in the direction indicated in the figure. Figure 9.1, a very long train traveling at a speed v on a straight railroad track embankment. The points A and B indicate the two locations where the lightning strikes occur. The points M and M' represent their middle points with respect to the railroad embankment and to the train, respectively. For the people who are traveling inside a passenger car of this train, it will be more natural and advantageous to use the train as a rigid body of reference, or an inertial frame of reference. They can relate all events to the train instead of the railroad embankment, and not just the events happening inside the car, but all other events as well. As a matter of fact, every event that takes place along the railroad track can also be considered to be taking place at a certain point with respect to the traveling train's extended reference frame. The definition of simultaneity can also be given in relation to the train in exactly the same way as it is given in relation to the railroad embankment, as was done in the previous chapter. Naturally, then, the following question arises. Are two events, the two lightning strike events at two distant points A and B, which are simultaneous with respect to the railroad embankment, also simultaneous with respect to the moving train? The answer to this question must be a definite no. Let us see right away, without a moment's delay, why this should be so. First of all, when we say that the two events of the lightning strikes at two locations, A and B, respectively, are simultaneous with respect to the railroad embankment reference frame, we mean the following. The rays of light emanating from the lightning locations A and B come upon each other for the first time at the exact middle point M of the railroad section AB of the embankment. However, the locations A and B on the embankment of these two events also correspond to the same two locations on our very long train. Let M' be the middle point of the interval distance AB between these 2 points A and B on the traveling train. This point M' naturally coincides with the point M at the moment of the lightning strikes as judged from the embankment. This is because M and M' are defined in exactly the same way at that very moment. But as shown in the diagram, M' moves to the right with the speed v of the train with respect to the railroad embankment. If the train were not moving, then an observer sitting in the train at M' would be stationary, and he would remain permanently in the same location, M. In such a case, then, the rays of light emitted by the lightning strikes A and B would reach him at the same time, that is, these two rays would first meet right where he is. Now, in reality, when viewed from the railroad embankment, he is rapidly moving together with the train towards the beam of light coming from B, while he is moving ahead of and in the same direction of the beam of light coming from A. The man at M' on the moving train will therefore see the beam of light emanating from B earlier than the beam emanating from A. All observers who use the train as a reference frame must therefore come to the conclusion that the lightning strike at B occurred earlier than the lightning strike at A. We thus come to the following important conclusion. Two events that are simultaneous with respect to the railroad embankment are not simultaneous with respect to the train, and vice versa. Relativity of simultaneity. Each frame of reference, rigid body of reference, system of coordinates has its own particular time. A statement involving the time of an event will not make much sense unless the frame of reference to which the indication of time refers is therefore specified. Physics has always assumed, at least implicitly, that the meaning of the specific time information is absolute. That is, it has little to do with reference frames, or at least it is independent of the state of motion of any particular reference frame. This assumption is thus consistent with the Galileo-Newtonian mechanics, which is based on the Galilean principle of relativity. We have just seen, however, that this long-held assumption of the absoluteness of time is incompatible with our particular definition of simultaneity, and hence with our definition of time, which seem to us nevertheless most intuitive and natural. If we drop the Galileo-Newtonian assumption of absolute time on the other hand, then the apparent conflict between the law of the propagation of light in empty space and the special principle of relativity, which we discussed in Chapter 7, ceases to be an issue. The considerations of Chapter 6, regarding the rules of adding velocities in classical mechanics, which led us to that conflict in the first place, can no longer be justified at this point. In that chapter, we concluded that the man on the train who traverses the distance, w, in 1 second relative to the moving train, also traverses this same distance in 1 second relative to the railroad embankment. But according to the above considerations, the duration of time of a certain process which is measured with respect to one reference frame, e.g., the moving train in our example, cannot be equated with the time duration of the same process with respect to a different reference frame, e.g., the railroad embankment. Hence, now we know we cannot claim that the man, by walking with a speed, w on the train, covers the same distance, w, relative to the railroad embankment in a time which is equal to 1 second with respect to the embankment. In addition, the classical considerations of Chapter 6 are based on yet another assumption, which was always made, albeit implicitly, before the development of the special theory of relativity. This second assumption, regarding the concept of distance, now appears to be arbitrary as well, in the light of a more strict consideration. This is the topic of the next chapter. The translator's notes. In Chapter 8, Einstein described how to determine whether two events have occurred simultaneously in a given inertial reference frame. Or, in other words, how to determine whether two clocks are synchronous that are located at distant locations with respect to this inertial reference frame. This led to a procedure of synchronizing clocks, so that they all indicated the same time. Based on this procedure, Einstein then defined time with respect to the given reference frame. In this chapter, Einstein now asserts that this concept of simultaneity, and hence that of time, are both relative. A quick summary. In the previous chapter, we considered the concepts of time and simultaneity with respect to a specific body of reference, namely the railroad embankment. We now consider these concepts with respect to a different body of reference, e.g., a very long train which is in a uniform linear motion at velocity v relative to the railroad embankment. In fact, we can use exactly the same definitions of simultaneity and time for both the railroad embankment and the train. Now the question is, are the two events that are simultaneous relative to the railroad embankment also simultaneous relative to the train? Using the previous example of two lightning strikes at A and B along the railroad track with the exact middle point M, these two locations also correspond to 2 points on the train at the time of lightning strikes. At this exact moment, the middle point of A and B on the train, M', also corresponds to M. However, M' is moving to the right toward B, with the speed v of the train relative to the railroad embankment where the two locations A and B are specified. The man at M' on the moving train will therefore see the beam of light emanating from B earlier than the beam emanating from A. All observers who use the train as a reference body must therefore come to the conclusion that the lightning strike at B occurred earlier than lightning strike at A. Therefore, each reference frame has its own specific notion of time. A statement involving the time of an event will not make much sense unless the reference frame to which the indication of time refers is specified. Hence, now we know that with respect to the example of Chapter 6, we cannot claim that the man, by walking with a speed w on the train, covers the same distance, w, relative to the railroad embankment in a time which is equal to 1 second with respect to the embankment. Qualitative understanding first. Modern physics is a quantitative science, as emphasized before. Even if you come up with a fantastic new way to understand nature, if you cannot provide some concrete numbers that can be verified in experiments, for example, your theory is not real physics. But that does not mean that qualitative understanding is not important. In fact, qualitative always precedes, or should precede, quantitative. Without qualitative understanding of a given problem or physical phenomenon, quantitative is pretty much useless for the theoretical physicist. Or at least, that is how the translator views the philosophy of Einstein when it comes to theoretical physics. Although this statement may sound mundane enough, it is in fact in a sharp contrast with the current practice in physics. Theoretical physics means mathematics in the modern times. Equations will reveal the truth about nature. We use the phrase equation worshipping to refer to such a culture. Ironically, Einstein did not even trust his own equations, namely his namesake gravitational field equations. When people came up with an expanding universe solution for his equations, he took it with a skepticism. When black holes and gravitational waves, etc., were predicted by his theory, again his first reaction was skepticism. He knew that his equations were just equations. In the modern times, his equations are worshipped by many physicists. That seems to be the ultimate irony. Einstein devoted his entire life fighting everything authoritarian in and out of science, but his theories, especially general relativity, now carry a strong overtone of authority. When Einstein started working on general relativity, he relied on his physical intuitions first. For example, he already predicted the bending of light qualitatively many years before he completed his equations. The problem of Mercury perihelion anomaly, etc., were all studied before he came up with equations. This is in an absolute contrast with the modern tendency where theoretical physicists start with equations and try to understand nature based on what the equations tell them. The majority of the foundational physics community think that purely mathematical theories like string theory are real physics, and they seem to really believe that mathematics will truly lead them to the ultimate truth. In this book, Einstein does not go directly to time dilation, etc., which is really easy to compute at this point, e.g., using the Lorentz-Einstein transformation equations. Regarding time, for instance, Einstein gradually introduces this concept, e.g., in Chapter 3, Chapter 8, and this chapter. Even in this chapter, he emphasizes first the qualitative fact that time is relative, even before he talks about what exactly this means, say, in terms of more precise equations. The quantitative discussion, which is in the scheme of things not that important, is deferred to Chapter 12. Quantitative understanding is much more important, and in fact, much more difficult to attain than just dealing with numbers or equations. Einstein's definition of time. Let's quickly review what we learned in Chapter 8 first. Time at a given location is what we measure with a clock, according to Einstein. A clock has a moving part, e.g., a hand of an analog clock. The motion of this moving part indicates the passage of time. When defining time over an extended space, there are two additional requirements. First, we need to put a lot of clocks in space, with respect to a reference frame. This is because it takes time for light to travel a distance. Second, we need to synchronize them so that we can have a universal definition of time, at least relative to the given reference frame. Simultaneity. Since we live in a world where things are spread over space, how do we compare time across distant locations? Essential to this question is the concept of the same time, or simultaneity. So first of all, how can you tell if the times of two events at two different locations are the same? Einstein proposes that given two distant events, if the event signals reach their middle point in space at the same time at this particular location, then these two events are supposed to have happened at the same time across these two different locations. Clock synchronization. Now that we know how to determine if two events are simultaneous or not, or if they happened at the same time, we can use this method to synchronize two or more clocks which are located at distant locations, but which are at rest relative to each other. In particular, we adjust the two given clocks so that the same event, e.g., the two clocks hitting the same 12 o'clock happening with respect to these two clocks are simultaneous. Then we say that these two clocks are synchronized at the time of these two same events. As stated, we need to put a lot of clocks over the area where we need to measure time with respect to a given inertial frame and synchronize them all before we can use the measured time values in this particular area. In this sense, a clock does not exist in isolation in Einstein's world. A clock really means a swarm of clocks which are distributed over space, and which are all synchronized according to Einstein's clock synchronization scheme. The identical clock hypothesis. Now, once two identical clocks are synchronized at a certain time, they remain synchronized at all time, as long as they are at rest relative to each other with respect to the same inertial frame. This is because we assume that identical clocks run at the same rate, regardless of where they are located and regardless of when they are compared. This is a hypothesis in that nobody can prove this. This is assumed to be true unless and until proven otherwise. Physical measurement of time. Now, based on this preparation in a given reference frame, we can assign a time value to any event with respect to this reference frame. For a given event, we pick the clock which is closest to the location of the event. The time reading of this clock is the time of this event, again, with respect to this particular reference frame. Equation of the same time. In the previous chapter, we mentioned the equation of light and the equation of simultaneity with respect to an inertial frame of reference, both of which turned out to be rather trivial. Let's quickly go over these concepts again before we review the concept of relativity of time of this chapter. Given two events, when we say that these two events are simultaneous with respect to an inertial frame of reference, it means that the times of these two events, t sub 1 and t sub 2, respectively, are the same with respect to this inertial frame. That is, t sub 1 equals t sub 2 equals some constant. Again, time is always defined relative to a reference frame, and this fact is always implicit when we talk about time. Hence, even this simple equation should be understood with that in mind. Now, for any event with time t sub e that is simultaneous with either of these two events, it also holds. T sub e equals t sub 1 equals t sub 2 equals the same constant. Hence, we are led to the following equation. T equals constant. For any arbitrary event with a time coordinate t that is simultaneous with these two events. Note that this equation really represents a set of equations, in fact, an infinite number of them, depending on the value of the const. As stated before, this seems so trivial. We spent so much energy defining simultaneity, synchronizing clocks, and so on, and after all that, we arrive at what appears to be simply a set of equations defining coordinate values for t. We can make a few comments on this point. First, it looks trivial because the time coordinate has been incorporated into a certain way, in hindsight, into the Cartesian coordinate system. As mentioned, this was based on the insights of Einstein and Minkowski. As we will see shortly, in fact, it is not as trivial as it looks. Second, in a way, it validates Einstein's clock synchronization method. According to his physical definition of simultaneity, or of the same time, we are indeed led to the mathematical equation of the same time. T equals constant. However trivial it may look to us. Hence it proves that Einstein's method is not some wacky method, but it indeed corresponds to our intuitive notion of time, at least in this simple case, that is, stationary clocks. Third, and probably most importantly, Einstein's physical definition can be extended to a more general case of, say, moving clocks, as discussed in this chapter. On the other hand, with the mathematical equation alone, t equals constant, we have no way to even guess how to generalize this equation. For illustration, here's a simple space-time diagram, showing the equations of the same time in the CT-X coordinate system. Figure. The spaces of the same time. There are 4 events shown in the TX coordinate system, each with an associated light cone. 2 of them on the left and 2 on the right are simultaneous to each other, respectively. The lines connecting these simultaneous events are parallel to the x-axis. Any event lying on each of these lines are indeed simultaneous to the respective 2 events. Note that the equations of light cones in this 1 plus 1 dimensional space all have the following forms. X minus x sub 0 squared equals c squared t minus t sub 0 squared, where x sub 0 and t sub 0 are arbitrary constants. The point t sub 0, x sub 0 corresponds to the apex of a given light cone. As stated before, due to the translational symmetry, both in space and time, the choice of the origin of a coordinate system is entirely arbitrary. Hence, it is often convenient to set t sub 0, x sub 0 equals 0, 0, unless we have to deal with multiple light cones, which leads to the equation of light that we showed in the last chapter. X squared equals c squared t squared. Relativity of simultaneity. This is the first time we truly use the word relative in this book, beyond the use of this word in the principle of relativity. After some long preamble, let's finally talk about what Einstein teaches in this chapter. The concepts of simultaneity and time, as defined by Einstein, are relative, that is, relative to a given inertial observer or reference frame. Einstein uses the moving train, which is moving at speed, v, relative to the railroad embankment, to illustrate this point. This is replicated in the following diagrams. Figure. Events that are simultaneous to one observer may not be simultaneous relative to a different observer. In the left-hand side figure A, the observer M, who is located in the middle point of the two lightning events, A and B, is shown. This observer is stationary with respect to the railroad embankment, and hence it is shown as if it is moving vertically upward, in the direction of time. Note that its x-coordinate value does not change, since it is at rest with respect to the reference frame, or the coordinate system. The lightning flashes at A and B meet at the point, or event, denoted with P, whose spatial location is the same as M. And hence the events A and B are simultaneous in this reference frame. In figure B, the observer M', who is moving with the train, is shown. M' happened to be the same as the middle point M between A and B when the lightning event occurred, relative to the railroad embankment reference frame. But as Einstein explains, since the train is moving, that is no longer true as time passes again when viewed from the railroad embankment reference frame. Because the train is moving at speed, v, M' moves with v as well, which is indicated as a tilted vertical line in this diagram. The equation of this motion is Vt equals x, or equivalently, v over c ct equals x, where v over c is a dimensionless constant and ct has the dimension of distance, since the dimension of speed is distance over time. As explained before, by using ct instead of t, the light cone has a slope of plus or minus 1 in the spacetime diagram, which can be rather convenient. As shown in the diagram B, the moving observer M' sees the lightning flash of the event B first at p sub 1, before he sees the lightning flash from A at p sub 2. That is to say, these two events A and B are not simultaneous with respect to the moving train reference frame. In other words, the clock times of these two events are not the same with respect to the clocks of the train frame. Hence, as Einstein explains, simultaneity is relative. Now we can go a bit further. What would simultaneity look like, relative to the moving train? Equations of simultaneity for a moving train. Let us now take a look at the equations of the same time for the moving train, but still with respect to the railroad embankment frame of reference system of coordinates. Figure. Events with the same time. With respect to the embankment reference frame, the two events A and B are simultaneous, which means that the observer M at the middle point sees the two lightning flashes at the same time. This is reproduced in figure A. Now, what events will the observer M' of the train see as simultaneous when compared with the event A? One example is shown as an event B' in figure B. In fact, events from the line connecting A and B' will all be simultaneous to A. This is a qualitative statement. The lightning flashes or otherwise event signals which propagate at speed c meet at the point M', which is moving at the speed v together with the train. Hence A and B' are simultaneous with respect to the train reference frame. With respect to the railroad embankment frame, figure A, the line connecting A and B is the line of the same time, as far as these two events are concerned. The equation of this line is, as shown earlier, t equals t sub s. Using the symbol shown in the figure, If we choose the coordinate system in such a way that the event A goes through its origin, t sub s equals 0, then the line becomes coinciding with the x-axis, and this equation becomes t equals 0, which simply means that along this line time is t equals 0, regardless of its position x. Now the question of the day is, what would be the equation of the same time t prime sub s in figure B, that is the equation of the straight line connecting the two events A and B prime? We strongly encourage the reader to think about this problem. In terms of math, it is not a difficult problem. But conceptually, it may not be an easy problem. Remember, relativity of simultaneity is, as mentioned, at the heart of special relativity. If you can solve this problem, then you are at the level of Einstein, as of 120 years ago. We will relegate its derivation to the appendix, Appendix B, and here's the equations. Ct minus v over c x equals constant. Again, this represents a set of an infinite number of lines, or n-1-dimensional hypersurfaces in an n-dimensional space in general, which are all parallel to each other. As a matter of fact, by continuously varying the value of const, we can fill the entire two-dimensional, or n-dimensional space. Can you visualize this in your mind? By selecting a particular value of const, the equation of simultaneity can be made as follows. Ct minus v over c x equals 0. This line passes through the origin. Note, however, that unlike in the case of the stationary clocks on the railroad embankment, when viewed from the railroad embankment, Ct equals 0. The times of the moving clocks on the train, again, when viewed from the railroad embankment, have dependency on their positions, x. This is at the heart of the physics of relativity of simultaneity. Note that the lines of simultaneity for the moving train, with respect to the railroad embankment reference frame, are all little bit tilted upward to the right, with v greater than 0. Refer to the previous diagram B, for example, to make sure that you understand this. Note that when v approaches 0, that is, when the train slows down to a halt, this set of equations of simultaneity all become parallel to the x-axis, as they should be. Try to visualize this in your mind. Clock synchronization. Figure. Synchronize clocks at rest. Note that all clocks in each set, 2 sets are shown here, point to the same time. Now that we know what it means by at the same time, for both railroad embankment and the moving train, we can synchronize all clocks with respect to the railroad embankment and the train respectively, using the same synchronization method as before. The above diagram shows the synchronized clocks with respect to the railroad embankment. Once synchronized, they all remain synchronized. The clocks moving with the train are shown in the diagram below. Synchronized clocks in motion. Note that they are drawn along the lines parallel to the same timeline of t sub s. Clearly, we are showing only a few of the clocks in this diagram, both along the x and t axes. Can you imagine what it would look like if we drew some clocks parallel to the x-axis? Although we are repeating this so many times, as any reader should have noticed, it is very important to note that this diagram is drawn with respect to the railroad embankment, although we are looking at the clocks on the moving train. From the moving train reference frame, all clocks moving with the train will exactly like the one stationary relative to the embankment when they are viewed from the embankment reference frame, the first diagram before this one. That is the principle of relativity. For reference, with a particular choice of the coordinate system, so that m' is at the origin of this coordinate system, the equation of motion of the train and a particular equation of simultaneity, which goes through x equals 0 at t equals 0, can be expressed as follows. X minus v over c ct equals 0. Ct minus v over c x equals 0. Note that they are symmetric, with x and ct interchanged. These two equations almost look like the mirror images to each other. Again, units are entirely arbitrary. Try to look at these equations with c equals 1. One interesting thing to note is that, while we don't feel anything strange about the equation of motion, x equals vt, which we all learn in high school, the equation of simultaneity, t equals vx, looks somewhat weird, likely to all of us. Why? Relativity of simultaneity. We mentioned earlier that relativity of simultaneity was not about time, or that it was not just about time. In fact, relativity of simultaneity is more about space than time. As we have just seen, the concept of the same time defines a space or a slice of space-time. Take a moment to think about what this statement means. Since the 1D parallel lines of simultaneity fill the entire 1 plus 1 dimensional space, each line can be viewed as a slice of the two-dimensional spacetime, representing a space. This is also true in the 3 plus 1 dimensional space. Each equation of the simultaneity for a given const value corresponds to a three-dimensional space. Since this set of parallel 3D spaces, each with a different const value, fills up the entire 4D space, this 3D space is really a slice of the 4D space, although it is hard to visualize this. This slicing is closely related to the concept known as foliation in differential geometry. Depending on the value of v, we end up with different foliations. This is such a bizarre concept, but it is what it is in the mathematical interpretation of special relativity. Bolts of lightning on the moving train. In Einstein's lighting thought experiment, as described in this book, the two lightning bolts hit the two locations A and B on the railroad embankment. Although the train is moving on the railroad, the lightning misses it. How lucky, you might say. Or are they? So what happens if two bolts of lightning hit two locations on the train, say, A' and B', rather than on the railroad embankment? What happens to our concept of simultaneity with respect to an observer on the embankment and another observer on the train? Appendix C. Or even weird, what happens if one bolt of lightning hits one location on the embankment, say, A, and another bolt hits another location on the train, say, B'? Does this question, as stated, even make sense to you? Even weirder, what happens if two bolts of lightning hit both the railroad and the train at the same time, say at A and A' and at B and B'? Now, who said that special relativity was easy? Time is personal. People who are not familiar with special relativity always say that everything is relative according to special relativity, in their view. As mentioned, that is a meaningless statement, if not downright wrong, partly because the word relative in relativity has distinctly different meanings than its common meanings in English, as in hot and cold are relative, or relativism of philosophy. The same goes with the statement, time is relative. This is a pretty much meaningless statement, without qualifying what relative means in this context. The translator always thought that time is personal was a better description, ever since he first learned special relativity many decades ago. He recently saw that Kip Thorne, one of the leading physicists in the field of general relativity, and Brian Cox, a popular British science communicator, using the same phrase, time is personal. Do you agree that it is more descriptive than time is relative, based on your understanding of this chapter? Now does not exist. Some readers may have heard people say that now does not exist, or that time is not real, etc. These are really pretty meaningless statements, since there are no universal and consensus definitions for time, now, reality, existence, and even is. When people say that now does not exist, what they usually mean is that the concept of now is relative, in the sense of special relativity. Or, if you prefer, now is personal, as we just alluded above. As we briefly mentioned in the beginning of this book, some people think that anything which is not objectively real, e.g., anything that cannot be commonly experienced, is not real. And hence, in that sense, such things do not exist. These are really philosophical questions. Aristotle, for example, thought that now or the present didn't exist because it was just too thin, if you will, sandwiched between the past and the present. As far as special relativity is concerned, now means the three-dimensional space or slice, which is possibly infinitely extended, at a certain moment in time, say t=0, and it does not just mean the now time. As we emphasized earlier in special relativity, clocks are distributed over space, and time really refers to the time with respect to a given inertial frame of reference, which is again assumed to be infinitely extended in space. The rate of the flow of time. Time, as far as relativity is concerned, has two components: the concept of simultaneity, e.g., delta t equals 0, and the rate of the flow of time. As for this latter concept, there are two aspects. The time for me flows at a certain constant rate for every one of us. The time for others, but viewed by me, can flow differently in various circumstances, which is generally called time dilation. We will briefly touch on these two topics here, for later reference. The fountain of time. Now here's a million-dollar question: why does time flow? Where does time come from? Einstein, for example, made the hypothesis that all identical clocks would run at the same rate anywhere and any time. But even before that, there is an even more fundamental hypothesis that we need to make. A clock runs. Why? Is it because time flows? Does the hand of a one-hand analog clock move because time flows? Or does time flow because the hand of a clock moves? This is something that very few people talk about, and it is very likely something that very few people even realize. But the most mysterious thing about time is that it passes by 1 second for the duration of 1 second for every one of us. And this rate of flow of time is the same for all of us. Why? Where does time come from? Time dilation. The concept of simultaneity is relative, which was the topic of this chapter. Hence, time is in general relative, since one of the two aforementioned components of time is relative. Although Einstein didn't explicitly mention in this chapter, the rate of the flow of time of others when viewed by us slows down in certain situations, and hence it is also relative. Time dilation due to the motion of a clock is discussed in Chapter 12. Time dilation due to acceleration and gravitation is discussed in the second part of this book. Does the moon exist when no one is looking at it? Here's an interesting semi-philosophical and semi-physical question. Einstein famously, likely rhetorically, asked if the moon existed even when no one was looking at it. This was in response to Bohr's interpretation of quantum mechanics. Generally, this question is related to the observer or measurement problem. Here's an interesting question. In this and the previous chapters, Einstein uses the middleman, so to speak, to define the concept of simultaneity. Now, what happens if this middleman doesn't exist? Can you still define simultaneity without a middleman? Or what happens if the middleman falls asleep or closes his eyes exactly at around the time when the light flashes from two locations, A and B, arrive at the middle point M? Did they still occur at the same time? Or should it just leave it as unknown? Why do we need this middleman in the first place? What do you think? What's next? Kinematics, the foundational part of mechanics, deals with space, time, and motion. In the previous two chapters, we saw that the concept of time is relative. In the next chapter, we will see that the concept of spatial distance is also relative. Chapter 10, Relativity of Distance in Space. Feynman lectures on physics. Special relativity is not a difficult theory from the standpoint of knowledge. In fact, the basics of special relativity has been taught for many decades now in the freshman-level general physics class for engineering and science students. If you are interested in the Cliff Note summary of special relativity, we recommend the Feynman lectures. The level is a little bit higher than that of most general physics textbooks, although the book is based on the lectures which were originally given almost 6 decades ago. But the style is rather unique, as is the case with all Feynman lectures. Furthermore, the whole book, in fact 3 books, is available online for free. Here's a list of relevant lectures or chapters, with the links to the respective web pages on the Caltech website. Volume 1. Chapter 5. Time and Distance. Chapter 11. Vectors. Chapter 15. The Special Theory of Relativity. Chapter 16. Relativistic Energy and Momentum. Chapter 17. Spacetime. Volume 2. Chapter 31. Tensors. Chapter 42. Curve space. The Einstein's Books Project. We are working on new translations of some of the more important writings of Einstein into English. Your purchase of this book supports our effort. This book is not available on Amazon.